Hi, everybody. Welcome to another exciting microcontrollers class. Let me see if we can share the screen on this thing. It's always a challenge to get things started. Share screen and desktop share. Okay, you should be seeing the screen now. Hopefully everybody's able to see it okay. Let me rearrange things a little bit. Okay. So what I thought I would do is try and review a little bit of what went on in the lab yesterday. So in our last exciting microcontrollers class, we were using the section of the microcontroller known as the ADC converter, and you can see that here highlighted. It's got a couple of external inputs, a ground, an analog reference, and some analog VCC input. And these can all be seen external. Can you see it okay?
Yes.
Okay. So we can see all of these things external. And when you see it external to the dotted line, that represents pins that you can actually access. That is to say, there are connections to the chip from the outside world. We see analog to digital conversion inputs here, ADC 6 and 7, and that's true for some of the quad flat pack versions, not for the parallel dip versions that you find in the Arduino Uno. So we're constrained to port C 0 through 6, which you can see over in here. They're tapped in and going over into the ADC converter. We can also use them as digital I/O ports, should we like to. We set up our data direction register for that, but right now we're just interested in using them as an ADC converter input. And that's sort of the focus of yesterday's lab. We were able to digitize from the ADC converter and then output to our little SPI DAC, and we did that in real time, changed our scaling rates for the sampling, and then proceeded to observe aliasing effects for different frequencies from our oscillator onto our oscilloscope. And that was all very educational and fun. So now let's try and dig a little deeper into the programming aspect of this. And I guess the lesson for today is you gotta read the fine manual, because if you don't, you're going to get really lost in the bit flipping stuff that you have to do to make things work. And what I'd like to do is I'd like to try and relate the programming that you have to do to the hardware that you're having to deal with. And so there's a couple of things going on in this diagram that really don't strike you as particularly obvious. Like here's a little block that says internal band gap and then analog comparator. What's that about, And then you can see the ADC converter feeds into this rather thick looking line. That's your data bus. So it can actually be read to and written to from the data bus. And there's a bunch of registers in here for controlling it. And we're going to examine some of those registers. So let's look deeper into the ADC converter now. And we can see there's a bit of logic going on here. There's this thing called ADMUX, which is the analog to digital converter multiplexer select register, right? And the register contains perhaps 4 bits for multiplexer inputs, but it also has other things, ADLAR, REFS0, REFS1. Now, what's that about? There's this other register here called the ADC control and status register A, and yes, indeed, there is a B, and it has things like ADEN and ADSC and ADFR and ADIF and all these prescaler inputs, which we were playing around with yesterday. And this is stuff that we have to sort of learn about. And then it has these outputs, ADIF, ADIE, and then it goes into some kind of an AND gate that says, aha, my conversion is complete. Let's generate an interrupt request. And that's kind of interesting. So then we look over here and we say, aha, clear ADLAR for 10-bit results. And that's kind of what we're doing here. We say clear bit, and here's in the ADX, clear the 80 LAR bit. So there's this one bit right in through here. We clear it, and that's going to give us 10-bit results somehow. And in fact, that's taken straight from our code here. Now we know why we're doing it. Let's take a look a little deeper into this ADC multiplexer register. But before we do, we see, oh, here's some more code over here. And it says set bit in the ADC SRA ADEN, which is the analog to digital converter enable. I guess you have to do that in order to be able to use the darn thing, because if you don't enable it, it just doesn't work. So this is kind of an interesting point. You know, this is, how would you know to do that? Well, got to read the directions. So let's dig a little deeper and see how all of this comes together. So here's a blow up of the analog to digital converter multiplexer register. So keep in mind, that's this thing right over in here. It's highlighted with the yellow. And here are the bits, right? For the 4 bits worth of multiplexer, we go bits 0 through 5. So we're only using the least significant 3 bits for selecting the multiplexer input. And keep in mind, there's only one analog to digital converter here. We just have to analog multiplex the input lines and choose which one we want to use when we want to do our conversion, because we can only convert one line at a time, because we only got one ADD converter, and that's it. And then there's this thing here which I snarfed from the data sheet, and it says there are these bits, and the most significant 2 bits of our 80 mux register, and they say, well, look, if you set it to 0, you use an external analog ref, and the internal ref is turned off. If you set it to 0, 1, you use the VCC with an external capacitor. And then there's a reserve thing, which we don't use at all, 1, 0. And then 1, 1, there's an internal voltage reference. And so what do I do? Here's my code. I set REF 0, so that makes this a 1. And then I clear REF S1, that makes this a 0. So 0, 1, and you can see what I wrote in here. I wrote VCC REFS in binary 0, 1. So 0, 1 means I'm going to do the VCC as my analog reference. And that's convenient because we always have power, but it's inconvenient in another sense, because if the power grid, if the power supply fluctuates just a little from 5.2 down to 4.8, it's going to throw off the whole ADD converter. And if our sensors output analog voltages or current, then it's going to throw off all our sensors too. So inaccuracy in something like a thermocouple will show up with an extraordinarily high variance in temperature. So if you have a need to have precision, this is not a good way to go unless you can be sure that you have a precise VCC. And we're never really that sure of our VCC. In fact, we could run it through a regulator and make, a common measurement, but it's really nice to know that there's this voltage reference here, and we can modify things a little bit if we want to do the voltage reference. So that's kind of neat. Right now, we don't care that much. We just want things to work. And so we're going to do the convenient thing. We're going to set REFS 0 and clear REFS 1. That gives us a 0, 1 and says, okay, let's use the VCC. So that's where that comes from. And you say, geez, Professor Lyon, this is too much detail. We don't need to know all this detail. Yes, you do. And the reason why is because if you don't do this stuff, it just doesn't work. This is not like a compiler error. It's either going to work or it's not going to work. And when it doesn't work, you won't know why. So having these directions in the code kind of makes sense. It lets you know what you're doing. Trouble is, I can't get these pictures into the code. So putting it together in a PowerPoint actually makes it better in a big way. So here it is, the 80 mux again, right? We saw REF 0 and REFS 1. And now we can use our knowledge of digital design 1 and electronics to try and relate our code to what's going on. REFS 0 was set to a 1. That's the gate to a little MOSFET, and that's going to let voltage pass through because a MOSFET is a voltage variable resistor. And so what it's doing is it's letting this little 2-to-1 multiplexer go and assert a line going into the 10-bit DAC. And that is your voltage reference input. And you can see how an analog reference, if left unconnected, will be overridden by whatever comes out of this 2-to-1 multiplexer. And then with a 0 being written into REF S1, we can see the 2-to-1 multiplexer is going to select leg 0, which is AVCC. And now you can relate that back to the code, which says we're going to clear REF S1, that's this leg of the multiplexer, and we're going to set SBI RFS0, that's this little gate input to the FET, the field effect transistor, and that's what allows us to use 0-1 with the external capacitor at REF pin. Now, put a nice external capacitor in there, and that's going to keep the voltage up somewhat. That's why they're asking for an external capacitor, because they figure if there's fluctuations in the line, they shouldn't propagate to the DAC. So if we're not using an external capacitor, and we're not, then it turns out we are in the we don't care, it's good enough for us kind of camp. And that's all right if all you want to do is digitize, you know, an analog signal. But now you can see how the bits actually relate to underlying hardware and how they route signals around by setting up this little 0-1 versus 0-0 thing. So that's kind of cool, actually. And you can see why 0-0 might give you the analog reference. That turns off this gate, and it gives you a direct outside reference. You see these square pads? That means you can wire to that. There's like a pin on your Arduino Uno. You can actually connect something to this. And that'll give you, if you have a nice stable analog reference, an input to your 10-bit DAC. And that might be cool, especially if you said to me, well, I know that my input is going to range from -1 to +1 volts. Therefore, I want an analog reference that's consistent with that, and I'm going to let the DAC float and digitize something coming right out of my guitar preamp or something like this. So then you could say, aha, I'm going to set my analog reference the way I want it. And that might be a reasonable thing to do. So that's a nice blow-up diagram of what's going on, and it lets you get a little bit of insight into why you're doing what you're doing, because otherwise it just seems like magic, and it shouldn't seem like magic. It should just be something you can relate to directly from your digital design class. And you kind of can, I think. It's a sort of an interesting idea. Let's look again at some of the code and look at the diagrams. So here's this multiplexer register, ADMUX. And it says here there's an ADLAR bit, just one bit in this multiplexer register. So it's not really about multiplexing so much as it is about control. And so that means it's going to do some sort of right adjusted for 10-bit results or left adjusted for 8-bit results. And then you get your results. These will be the 8-bit register. And if you want the 10 bits, you'll need both these registers, which are read into a variable called ADC. And so what you do, this is what we've been doing, is we want to go and clear the ADLAR to right adjust 10 bits. And so the most significant 2 bits are going to be in an ADCH, and the least significant 8 bits will be in ADCL, and we'll get the whole 10 bits in a variable called ADC. And so what we do in here is we say clear the ADLAR, which means clear this bit, bit 5, and then we're going to get our 10-bit results. That's what we want, the nice high dynamic range results. We can go faster if we only want 8-bit results, but we're going to get 10-bit results. And so that's fine. And that's where that comes from, ADLAR. So if we go back and we take a look and you say, well, where is this ADLAR? I don't see it. Let's take a look at the next line. It should be in there somewhere, I think. Oops. Sorry about that. ADLAR. I am not seeing that. But it should be part of, oh, there it is. ADLAR goes into the conversion logic. So that's coming right out of the AD multiplexer. So there's bits, I think these are bits 7, 6, 5, 4, 3, 2, 1. I think we're skipping a bit. There's one bit that's not used. Yep, there it is. Bit 4 is reserved for future use, they say. I don't know if they're ever going to use it, but there it is. So that's where ADLAR comes in. to play. And then there's this other thing, the multiplexers. Well, we're just going to either have it set all zeros, or we're going to put a 1 in for the least significant bit. So if we're in the middle of sampling ADC 1, then what we're going to do is we're going to go and set mux 0. Otherwise, we're going to clear mux 0. So if we're alternating between mux 0 and mux 1, we alternate between setting and clearing. There's another way to do this. If you said, oh, well, I'm going to have, perhaps 5 or 7 different multiplexer lines, I could clear the least significant 4 bits by ANDing with 4 bits that are 0 in the least significant nibble, and then ANDing with 4 bits that are 1 in the most significant nibble. That's 0x f0. And this comes from your bitwise ANDing. The ampersand is bitwise. And then comes a bitwise inclusive OR. Take the least significant 4 bits from the ADC number that's passed in and put them into the least significant 4 bits here. So now you can see where your sort of Boolean algebra is coming into play. And with 0, it makes it 0. Or with the ADC number, and it's going to set the least significant bits. And so that's kind of cool. As long as you want to do something like that, this might be a reasonable line of code. But if you're only alternating between 2 ADD converters in 2 multiplexer settings, this is actually a more efficient way to go by at least a clock cycle or something like this, maybe 2. So then, and to that point, I should mention to you, when you read the data sheet on this, it says if you have a 20 megahertz clock on your Mega 328P, you have 20 MIPS, 20 million instructions per second. When you have a 16 megahertz clock like we do, you have 16 million instructions per second. So our clock rate directly links to our architecture, which is a single instruction, single data, or SysD type architecture. So if you make this chip faster, it's going to go faster. There's not multi-cores. There's nothing fancy going on. In fact, it's an 8-bit toaster controller. So here's another little flag for you called ADATE. I had to look this up because I keep forgetting what it stands for. That's the Analog to Digital Converter Auto Trigger Enable, ATE. I mean, this is like worse than NASA. Right, NASA has like SRB for solid rocket boosters. Here's ATE for Auto Trigger Enable. And so the ADATE has to be set. You say, well, why is that? You can say, well, because look at this AND gate. If ADATE is set, then the one leg of the AND gate is now enabled. And here's a little bit of code that says SBI ADATE, and that's going to set the ADATE for that leg of the AND gate. Just pretty cool, pretty cool. So now you've got automatic triggering enabled. That's nice. That's going to start the count from 0 on the prescaler in order to make everything consistent. And then it's going to detect a rising edge coming out of this analog multiplexer here. And this is the ADTS. Oh my God, what are these guys thinking? And so the DTS is a trigger select. That's the analog to digital converter trigger select. And if you do something like set it to 0, set the 3 bits, the 3 least significant bits in the register to 0, then it's going to take this multiplexer and get the first input, which is called, wait for it, ADIF. I was like, oh man. And here's another one to know. That's the ADC interrupt flag. So when this thing is done converting, it's going to create a rising edge on the interrupt flag. It's going to get ANDed with the auto trigger enable bit, and then that's going to start your conversion, which is cool. There's another thing here called ADSC, which is ORed with all of that, and you can start the conversion manually just by asserting the ADSC for start conversion line, and that'll get your conversion to start as well. So over in here where I said, look, ADC SRB, that's the analog to digital converter, I think it's called status register is set equal to 0. So the least significant bits include ADTS 0 through 2. That gives us the ADIF input, which is the interrupt flag, so that when this thing is done doing its conversion, we should be able to get the conversion logic provided A date, which I've set, is set to true, and then we'll get conversion logic to start converting for us. So that's where we get some of that code there. It's not obvious, right? I mean, you look at the diagram, it becomes a little bit more clear, but you really have to think about this stuff. And so here comes the ADC SRB. Status register B. That's it, status register. I always forget. So there's a status register A and a status register B for the ADC. And here are the data selects, and you can choose any one 0 through 3. And then there's this little chart in here which says, look, you can make it free running mode. That's what mode, which I set to 0. So that's where you get is free running. You can use an analog comparator, which is really good if you're trying to like build an oscilloscope out of your Arduino, because the analog comparator can check something on like the rising edge of something or other and then trigger. So this could be like a variable trigger input, which you use on your little oscilloscope. And you could have the Arduino act as an oscilloscope. You could somehow devise external interrupts that are going to do conversions, or this is very common, you can use counters. The first counter 0, is like an 8-bit counter, and the next counter 1, is a 16-bit counter, so one's a higher precision than the other. And so you could use counters to trigger the conversion for the analog to digital converter. But we're doing free running mode right now, and that works fine, because when the converter's done, we're going to go right in and start to take that data and output it to our DAC. So we're going to let it run as fast as it can. And if we change our prescaler in order to change the conversion speed, that's going to change the overall throughput of our system. And we've seen how that impacts the quality of the output that we get. It's a big deal. In fact, the way you hear it is a big deal. So and also what it looks like is a big deal. So it's sort of an important quality control factor. And so that's my basic coverage of the code. Now, when you look at the code, it becomes way more clear what's going on, right? Because now when you say, if we're sampling ADC1, we're going to set mux bit 1 to ensure that we're sampling ADC1. Otherwise, we're going to sample ADC0, and we do a clear on mux bit 0. So that's cool, right? And it shows you exactly how we get to where we're getting. Here's the A date, and here's the trigger select bits, TS, ADTS, analog digital converter trigger select. And so we can see why these things are set or how they're set. And in fact, if we go to the head of our code, we can see the ADC SRB is being set to 0 because we want the auto trigger select to be ADIF to show when we're finished with the conversion. So that's kind of cool. Here's the ref 0, 1 and 0, and you can see where we put in a 0, 1 for REFS 1 and REFS 0. That sets our reference voltage to VCC. Here's our bit 5 ADLAR, and what that's doing is it's going to clear the ADLAR bit in order to give us a 10-bit result from our ADD converter. That means we'll be able to grab a variable called ADC every time we're interrupted. We go over in here, and we can see we've got to enable the ADD converter. So we go to the control register, and then we enable ADD converter input. Otherwise, we can't do anything. And then we take a look at this prescaler. And someone said to me in the class, he said, oh, but look, it runs faster if we give it like, I don't know, a 2 megahertz clock for the ADD converter. And I'm like, yeah, sure, it runs faster, but if you read the directions, what it says is Frequencies up to 1 megahertz do not reduce the ADC resolution significantly, but operating the ADC with frequencies greater than 1 megahertz is not characterized. I can't tell you how many YouTube videos I saw where people were using 2 megahertz inputs into their ADD converters without mentioning the fact that they have no idea what the resolution is. I mean, it's supposed to be 10 bits. As far as I know, it could be down to 9 bits, 8 bits, 6 bits. Take your pick. Who knows? And not characterized means they don't really care what you do if you want to do that. It's not going to blow anything up, but don't expect it to give you a full 10 bits worth of accuracy. So this is a kind of an interesting point. People kind of ignore the data sheets on this, and it's a little bit maddening. I'm like, why wouldn't they read that? And maybe because they don't read the data sheets, huh? So then it says for optimum performance, ADC clock should not exceed 200 kilohertz. You know, and I'm thinking to myself, 200 kilohertz, that's like nothing. That means I'm going to be down in the, I don't know, 9.6 kilohertz sample rate, because that's 125 kilohertz. Next one up is 250 kilohertz. So that doesn't really float my boat, because if I'm sampling at 9.6 kilohertz across two different ADD converters, I'm really down to a total sample rate for each converter of perhaps 4.8 kilohertz. And that means my maximum clock frequency, my maximum input frequency, according to Nyquist, is going to be half of that, which would be 2.4 kilohertz. And I really want audio to go up above 2.4 kilohertz. So if you're trying to sample from more than one ADD converter and you're splitting the operating rates in this way, you really can't settle for 200 kilohertz. I don't feel it's going to, you don't get good results. I've heard it. It sounds terrible. So, you know, going to a megahertz, that's fine. If you go to a megahertz, then you've got 76.8. If you want to split it in two, you'll have 35 kilohertz. That gives you Nyquist, which will probably bring you up to about 16K, which is fine. 16K sample rates, 16K of fundamental frequency into a 35K sample rate. That's fine. So here I am doing a divide by 16. And so I'm dividing the system clock by 16. And so what that means to me is I'm going to have a conversion clock for the ADD converter of perhaps 1 megahertz, which is exactly the kind of thing I'm looking for, because that means I've got my 76.8 kilohertz divided amongst the two ADD converters. So that's actually pretty good for me. And it shows you the trade-off, right? Because if you wanted to go to, let's say, 4 ADD converters, you'd have to take that 76 kilohertz and divide it by 4, because they'd each get the same rate of sampling. So that's a trade-off. Here's the interrupt enable. That's part of that input to the AND gate that enables interrupts to occur. And then we have this other thing, which is, I forget what it's called now. Oh, the trigger enable. And then I do my sample ADC is true, sample 1 is true. That's my flag that does alternation. And then I go through my start conversion. And at the end of start conversion, where we select the 80 mux, we assert the ADSC, or start conversion line, and that lets us begin our next conversion. So that's cool. And then you get interrupts, and they take an ADC vector on input. And now if we're sampling ADC1, we grab the ADC1 and we want to start conversion on 0. And when we write it out, we know we've got a 10-bit ADD conversion, but we've got a 12-bit DAC. So I take the 10 bits and I shift it over 2 bits, because I want to use the full 12 bits when I write out to the DAC and get the full volume. And then if I'm grabbing ADC 0, I just grab that and put it into a variable which I can use for processing later, such as modifying the volume if I like. and then I go through and start conversion on the next leg. Next time this thing's going to start, it'll be after I do the ADSC assertion. And now I'm alternating between sampling ADC1 and sampling ADC0. So there's my little flag, and that's the bang sample ADC1. And that's the code. Now, having said all of that, I know it's a lot, but this is the kind of thing you have to go through in order to run the ADD converter. Having said that, I've made this program much longer because I've added, globs of words from the data sheet so that you could see what's going on. Because going back and forth to the data sheet is a bit of a pain. And not to put too fine a point on it, let me just show you what's going on. Here is the actual data sheet that I've been using to guide me through the lecture. And so what you can do here is you can see this is the analog comparator control register. We didn't get there. But here's the ADC SRB, analog to digital converter control and status register B. And here is the ADTS lines, which are going to do the selector for the input. And so that's where you get that stuff. If you really want to learn how to use a chip and learn how to program it properly, you got to read the data sheet. And here's some interesting stuff about, this is detail about the band gap reference that they have. And these little guys in here are analog switches that lets you take a band gap reference and use that relative to an analog input and do a comparator. And there's all kinds of interesting stuff we can do to talk about analog comparators and how that can be used to trigger our ADD converter input. So that's the data sheet. It's, there for you to read. It's a lot, really. I mean, this whole data sheet is 662 pages long, and that's for one chip, right? So that's, how can I say it? That's a lot. I don't know how else to say it. If you wanted to, you could find stuff in here, like you could look up ADMux, and you could probably find that in several places. Here's here's the ADMux in the ADD converter diagram. So that's a pretty cool way to look at it. I think when you look at hardware and relate it directly to the software, you're in an area which is neither hardware nor software, but it's in between the two. And this is kind of where you would find like real product development. You want to write a driver for a new chip, this is the way to do it. You want to build a new device for a biomedical application, this is the way to do it. You don't just have these things fall out of the sky. You've got to like read the data sheets and figure out how to get things to work. And that's the secret to unlocking value for these sorts of devices. And so how many pages does it take to describe an ADD converter inside of a microcontroller? Well, that's a good question. This page is page 246, and it keeps going and going and going. And voltage references, 246. And he's got temperature compensations, comparators, and all these other interesting things. Let's keep going. 246, he's not done yet. Yeah, now he's done. So 261. So a little less than 20 pages, perhaps 15 pages to read, but it's dense. And that's the upshot of all of that. So are there any questions about the ADD conversion process? I just thought that was a nice way to go here for ADD conversion. I hope you liked my little presentation there, and hope you found yesterday's lab educational. So now let's move on to other things, unless you have some questions. We have a homework due today. This is homework number 6. And I think we did a little detailed review of homework number 6 last time. Let's take a look at homework 6, shall we, just to make sure everybody's on the same page with that. And I'm going to set up homework 7 so it'll appear right after homework 6, which is due tonight. Has its deadline lapse. So you'll see homework 7 right away. So here's, let's just take a quick look at homework 6 and see how things look. I'll just hit continue. Let's see, what was the question? I think, all right, so you guys, you probably have seen \n. Do you know what that stands for? Anybody?
You mean left division?
That's a new line. Well, it says new line right there, but it's also known as form feed. And then there's this \r. What's that about? It says carriage return. Why do I need a carriage return and a form feed? Two separate characters. Any ideas on that?
One sec.
So what happens is, I don't know if you've ever seen one of these things. I can do that here. ASR 33. Just take a look. There it is. I used to use this one when I was your age. This is an electromechanical device, and I don't know if you can see it, but in here, there's a little area called the platen, and then there's this carriage. See, the carriage has got like a little type ball on it, and what it does is it advances the platen to get to the next line, and then the carriage goes all the way to the beginning. So advancing the platen, that's a line feed. Getting the carriage to go all the way to the beginning, that's a carriage return. So you do line feed first and then carriage return. Actually, you do carriage return and then line feed, because carriage return takes longer. These things would print at 10 characters per second, but they had the added advantage of also being able to punch out paper tape, which would be good for long-term storage. I still have some paper tape in my garage somewhere. These were all the rage because you could do things like you could send a telex, send a telegram using these devices. And there's a little reader down here. You can see it's reading the paper tape. And as it reads the paper tape, it can print things out and also input it into the computer. It didn't use RS-232, the serial port. Instead, it used what's known as a 20 milliamp current loop. But you could get converters that would go from 20 milliamps to RS-232. I happen to have one. This one's particularly cool because it's got a little rotary dial phone in it. So you can do dial-up work if you need to get in remotely to a system. So this is really collector stuff. You don't see too many of these floating around anymore. So that's why you have carriage return and line feed, in case you were wondering. But they've made it into modern usage. Moreover, when you go to the Arduino monitor, and this is really maddening because it's still with us, right? The Arduino monitor, when you input something like here and you hit send, you can set it with a carriage return and a line feed, or just a carriage return, or just a line feed, or no new line ending at all. And if your code is sensitive to characters other than the characters you're expecting, and it sees like new line or carriage return or both, that could throw the program off. So when you look at the monitor, it's actually quite important that you take into account the fact that somebody could be turning in a new line or a carriage return or both, or you should specify that no new line endings are needed or should be wanted. And then when you go to get characters from the system, things will work properly. Otherwise, it'll be all messed up. So that's a sort of an interesting thing. Here we have a way to send binary versions of an integer. So integers have a low byte and a high byte, and you can send them 1 byte at a time. Or you can send the ASCII version with a carriage return. That carriage return is going to take up valuable overhead in transmitting the value. So does that make things more efficient when we send binary instead of sending ASCII with the carriage return? I guess we covered this already, didn't we? You guys are very quiet. Didn't we cover this last time in our last exciting microcontrollers class? Tell you what, I'll just...
We may have, I'm not sure.
Okay, I think the answer is yes, we did. And because I have a distinct recollection of having done that. And so, yes, true is correct. When you're sending binary data like this, it's more efficient than sending out the ASCII data. And then here's a sensor value coming in from an analog read line. The interrupt-driven stuff that we've done is way faster, right? I mean, we've seen that. We've taken the Prescaler, we cranked it up to 1 megahertz, we got 76 kilohertz sampling. This thing with this analog read is going to go about 1 sample every 115 microseconds, which is, I don't know how slow that is. Let's see. What's 1 million over 115? It's divided by 115. I'm doing it now. It's about 8 kilohertz, 8.6 kilohertz sampling. So it's, yeah, call it 9 kilohertz. It's bad news. Let's see now. There are 1,000 microseconds in a millisecond and 1,000 microseconds, 1 million microseconds in a second. That's true. So you should know your terms. Micros gets the number of microseconds since the arduino began running. With 4 microsecond resolution, we have a problem if you were trying to measure things down to the single digit microsecond. And I think we saw this as well. And here comes our good friend ADMux. And here's the reference, analog reference inputs. And if you put in 0, 1 into the most significant 2 bits, you're going to get the VCC as your reference. And we now know why. And here's the analog to digital converter control and status register A. And we now know what ADC SRA stands for. So that's cool. And now we've got more information about ADAT, right? So this is the auto trigger enable, ATE. Here's the interrupt flag, which is used to tell us whether a conversion is set or not, and can then be used to trigger a next conversion. Here's the interrupt enable, bit number 3, which is right there. And you can read it or write it, so you can tell if that's been enabled. And then here comes the prescaler bits. So prescaler bits, that's these least significant 3 bits, which we set up with a wide variety of, I guess, constants, right? So when we looked at our code, I think we saw the constants for that were part of the init right there. So there's our prescaler right in through here. And then we just set the ADC SRA. So that's dividing the system clock. And here's some nice examples of how you can compute what the period is for an ADC clock. But an 8 microsecond ADC clock is not the same thing as having an 8 microsecond sample time, right? Because we're actually inputting into a counter which is counting up to and down from the input signal until the DAC settles. So ADC clock frequency is 125 kilohertz, and we get that with the prescaler of 128. And you can even see the various frequencies. These are all done in tenths of a megahertz. So that's 0.125 megahertz or 125 kilohertz. So then here's question 7. And we could see, here's our good friends, the prescalers. We don't have all of them, but we have most. In fact, this is the maximum one you're supposed to use. That gives you a megahertz clock. And let's see what else we got in here. This is not as nicely documented as my other code, but he says, hey, wait a minute, I've got a 20 microsecond conversion time in here. So is that accurate? And the answer is, well, plus or minus 4 microseconds. So there's a problem. And then here's what we're doing here. We're doing start micros and then stop micros, and we're just storing the microseconds. And then we print out the conversion times. And so we get conversion times here are 4, 8, 4. It's not consistent, but micros is not that accurate. So that's true. And we know that now because micros are plus or minus 4 microseconds when we do the measurement. So here comes question 8. Is this review helping you guys? Shall we keep going?
Yes.
Oh, yes. Okay.
Yeah.
Yeah. So then here's a here's an analog read. This is not using the interrupt service routine like we were doing. But what he does do is he sets the prescaler up. And now he's got, 360 microseconds. How fast is that? That doesn't sound fast. Let's see. If I take 1,000,000, I'm using my little calculator here, and divide through by 360, because I'm too lazy to do this myself, it says I'm going at 2.7 kilohertz. So this is dead slow. Dead slow. And so why is it so slow, actually? That does seem slow, doesn't it? The following code will be more accurate because we were taking the same measurement 100 times. Oh, I see. I see. So he's computing, right? He's doing, right. We know we have plus or minus 4 microseconds. So if we take the output and divide it by 100, then we'll get an actual read of how long these things are taking. So that's interesting. And so 384 elapsed. What's this elapsed here? I'm not quite understanding why this values analog read. Oh, these are the actual values that you're reading. The start times are what you want. Start and stop times. That's what you want to print. Elapsed equals the stop time minus the start time. That makes sense. So elapsed equals 360 microseconds, and that's for 100? That sounds like a lot. Results times 100.
That's too long.
Is it? I mean,
Like...
if you take 360 microseconds and divide it by 100, you're getting 0.36 microseconds. That's really fast. Is that how I read this? Because his start times and elapsed and or is he doing this on a 1-for-1 basis? So he has 100 of these things. So each one is taking a snapshot. It does seem very long. I mean, I don't know. That does seem too long. You're right. So what was the question on this? The following code will be more accurate because we're taking the same measurement 100 times. Well, maybe so. Let's just take a quick look and see what the answer came out to be for that one. Because I'm looking at this and I'm going, maybe it should have averaged it. Would that have been better? I'm just going to go through and I'm going to say, and the answer is true on this one. But I'm thinking it's not the best way to measure it. But I'm not going to bore you with writing that code for you in real time right now because I'm not crazy about the science behind this one. Right. So he's doing this. Micros is inside of this loop. Then this is being run 100 times for each time micros is starting. And then he's going to stop. Right. So he actually did 100 reads. 100 reads. So it is divided by 100. Right? Because this loop is nested inside of this loop. So for every, and we ran this 10 times. So for every one of the start times that we have, we've run 100 analog reads. And what we're printing out should be the difference between the stop and the start. So we've got the value. That's fine. And then he says he's able to do this in 0.36 microseconds. I think the compiler optimized that somehow because that doesn't sound right. This is way, way too fast. But it says it's more accurate. That's the answer key, so I'll give you that. But I would look at that code really carefully before I made that decision and took it out and advertised it because you can't really rely upon that code. I'm thinking the compiler got in there and optimized the crap out of it. Let's look at this question. The following code will slow down because we sampled twice. Sampling multiple times is a great way to improve your signal-to-noise ratio, but it's also going to slow things down a little bit. Right, so here we are sampling two different things. That's going to slow things down quite a bit. And let's have a look. Yeah, that's true. Let's look at another one. The only way to encode text is ASCII. For example, the ASCII character for an exclamation point is number 33. Int this byte equals 33. Well, that may be true. This part is true. What about this part?
That is not true.
Yeah, that's not true. We already know as Java programmers, you can use Unicode. And in fact, if you're an IBM programmer, you can use EBCDIC, which is the extended binary coded decimal interchange code. And so there's more than one way to encode a character. It doesn't have to be ASCII. ASCII is kind of, I don't know, old. It's an old code. How old is ASCII? I have no idea, but it's old. I mean, if you wanted to, I suppose you could ask the Google, how old is ASCII? Yeah, see, okay, there must be a wiki on it, right? When did ASCII start? It must have been in the 60s, huh? Or before, maybe. Yeah, 68 is the standard. So it's a pretty old standard, I guess. It's an ASCII standard, and they give you the codes right over in here. And so if you wanted to, you could go in here and you could say, oh, yeah, here's the ASCII exclamation point, and it's hexadecimal 1, 2, which is, I think that's what it should be. Isn't that right? 1, 1, 2. Yeah, actually, I thought it was supposed to be 33, but if I take ASCII decimal 12, it's going to be, I'm sorry, hexadecimal 12, it's going to be 16 plus 2, which is 18. So it's not 33. I don't know why it says
Yeah,
33.
we know one is different.
Oh, wait. The most significant bit is up here. So that's actually 2, 1. So 2 would be 32 plus 1 is 33. Yep, that works. Most significant bits are on top. So it is 33. Cool. I think backslash is 92. Here's a backslash here. So that's going to be hexadecimal 5. A, B, I guess that's 5C. So that would be 16 to the 5th plus 12. 16 to the 5 plus 12 is probably, I don't know. Can I do this on this calculator? 16 doesn't have power. Shoot. Times equals 1, 2, 3. That's too big. I think my brain isn't working. Isn't that supposed to be the base? 16. Oh, 16 to the 1 times 5. I forgot my positional notation. Plus 12. So 16 times 5 is like a number. 80. And if I add 12 to that, that's a number. That's 92. So I was correct. So backslash is decimal 92, also known as 5C in hexadecimal. This is what I get for converting from hexadecimal to decimal in my head. You know, I get screwed up. Sorry about that. But it does work. So you can use your ASCII codes to do the conversions. Fancy. To write a byte in binary, you use serial write this byte. Serial write this byte. So that's good to know. Is that true, do you think? I mean, we've been using print, right? And print line. Now we've got a new one here, serial write. So now we can write out binary data, right? So that's what that's about. So serial write is going to work. It is part of the Arduino environment. You get serial.write. And you also get serial.print with an argument. And serial.print will let you print with the radix, right? So it says hex. Is that going to print out in base 8, do you think? Will this code print out base 8 or octal? I'm not just going to give you all the answers. You're going to have to participate a little bit, please.
I mean, can't you use serial print also with text?
Sure. So I mean, if you had some question, and you wanted to you know, do some sort of an example, you could probably do serial and you were asking, I think, before about 33, and you want to do it in hex. And I guess you could put in a print line. And you might want to do a serial begin over in here.
Yeah.
And then principal, that should print something like, I forgot what we said was in hex. 1C, was it? Let's see if that's true. Oh, we better do this in 9600 baud. And there it is, 2-1. 2-1. Right, because let's see, 2 times 16 is 32, plus 1 is 33. So that's certainly true. So then what would happen if you just took the print line and you put out 2-1? What would that print? It prints 2-1. What if you wanted the character? And then you printed out the character. Let's stop the auto scroll. I don't see anything in here. What if you did 92? That should work, right? Yep, there it is, backslash. So backslash is ASCII code 92. So that kind of works out. In fact, you can probably convert an arbitrary character like exclamation point into an actual number if you wanted. And that would give you, let's say, an integer. Now when you print the integer, you should be able to print out the number. There it is, 33, which is kind of what we thought. So that's pretty cool. Let's look at the next one. Oh, here it is, an octal. Oh, goody. So now we can kind of do radix conversion on our Arduinos. Does it print a binary string? Maybe we have to test it. So let's print it out in octal now. Somebody's writing on my my blackboard here. It's all right. And there it is, 4-1, octal, base 8. So does that work? Let's see, 4 times 8 is 32, plus 1 is 33. Yep, that works. So this is printing out an octal. So is this going to print a binary string? Well, we just got through showing how it prints out an octal. So the answer is no, it's not binary. It's base 8. So that's pretty cool. You guys got to participate here. Otherwise, you're going to make me feel bad about teaching or something. We'll give up and go to industry. So here it is in binary. Oh, boy. Let's try it in binary. I don't even know what that's going to be in binary. Oh, yes, I do. 4-1, it's going to be 1 0 0 0 0 0 0 1. Let's just see what happens. That should work, right? Oh, there it is. So that's exactly what we expected. And that's pretty cool. So it's all in binary. So that looks raw binary. That looks pretty true. Don't you think? Binary. Yeah. Here's one. Following code is going to print and then stop. What is this printing? It says here I can go and look at the ASCII table. I wonder if that URL is still good. I sometimes wonder about these things because my URLs change from time to time. I just never know. Oh, there it is. Oh, look, and we've got it in hexadecimal. Oh, how cool is that? We got it in decimal, hexadecimal, and octal, but we don't have it in binary. But if you had it in HTML, you could do ampersand $33, and that could emit an arbitrary character, which you may not be able to key in easily. And he's got these other very interesting looking characters in here. Shift out, shift in, data link escape. That's a good one. Negative acknowledgement. I like that. Let's see now. End of text, start of text. And there's a dog picture. Source lookup tables. So here's your ASCII. That's pretty cool. I like that. So let's see now. Prints out byte values in all possible formats as raw binary values as ASCII. Coded hex, octal, and binary values. So what do we got here? Print the ASCII cable map. First ASCII character that's visible is exclamation point. I guess that's why they start with that one. And it says serial this byte. This byte starts at 33, so it's going to print out an exclamation point. And then he says he's going to print it out in decimal. He's going to print it out in hex, and then in octal, and then in binary. Oh, this looks like a really good piece of code here. We need this code. I have to run this code. So let's just sort of slap it in there. What could possibly go wrong? Oh, I got the question in here. I'll go to the bottom, grab it. You can always do this if you're like wondering if the code works or if it, does what you think it does. Just run the code and see if it runs, see if it compiles. And there it is. The binary. It says it's going to run and then stop. It looks like it prints continuously, doesn't it? Keeps going. Auto scroll. Oh, I guess it does run and then stop. So now you've got all the ASCII characters being printed out and the binary, which is cool. So you don't have to do the conversion by hand. You can let the Arduino do it for you. Let that 8-bit toaster controller do the work. So that's cool. So that sounds like true. Let's see, serial available. Oh boy, what's that do? Returns true if the serial port is available. What do you think about that?
Let's try it.
Try it. Try see if serial port available works. Because if we do that, we could we Google it?
Yeah, but what's the fun in that?
What's the fun in Googling it?
I guess you could do that.
So let's find out. Okay, we'll just do the loop. Let's give it a go. Why not? Certainly, we are able to do these things. So we'll put in a setup, and we'll do a serial dot begin at 9600. And then what we'll do is we'll do a loop. And we'll have to say if the serial is available, it's greater than 0, means it's available. Then we'll read the next byte. And then we can print out the byte and decimal, maybe. And that'll print the decimal version of the byte. And it'll just keep going. So
you might. Oh wait, do you need to name the byte?
Oh yeah, good idea. Expected constructor. Oh, you have to declare this as void. Right? Got to do that. You got to do that for setup as well. Void. It has to return void. Stupid error. Done uploading. What could possibly go wrong? Ooh. A. And let's do, let's see, what was it going to be? Exclamation point. And you can see what he's doing here. He says 33, 13, and 10. Why? Because he's giving me carriage return and line feed. And sorry, line feed and carriage return. So let's do just the carriage return. That should be like a 10, right? And so here it is, 33 and 13. Now let's do no new line ending. Now you can see the exclamation point just makes a 33. So now A, B, whoops, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And now you can see that the letters are arranged in order. Isn't that cool? So 97, 98 through 122. So when you think about, lab 126 over at Amazon, that's because 1 is the first letter and 26 is letter number Z. So it's A through Z. Super secret, top secret lab in Amazon. Let's do that again. Only this time we'll do A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U. Uh-oh, I typed it wrong. U, V, W, X, Y, Z. See if that works. And it does, but in fact, what it does is it changes one bit. And so that makes things still sequential, but in a different numeric range. And that's ASCII for you. Very symmetric, very nice way to create a series of characters. And in fact, what you could do, if you were of a mind, is you could increment through all the different possible characters. So does serial avail work? Returns true if the serial port's available? And the answer is yeah, sure does look that way. So that was educational, wasn't it? Now you can,
That was cool.
Yeah, now you can input from the serial port, which is kind of important because maybe you could use that for something like controlling your waveform generator. Ooh. So here is some example code. Will that print the decimal version of B?
Professor.
Yeah, looks it.
For number 16, did you say that was true then?
Sorry, say it again.
For question 16, did you say that was true?
Question 16. We're going back now to serial available returns true if the serial port is available. Available returns the number of bytes available. That's what it really does. That's the number of bytes. So if the number of bytes available when you type in the enter is returned, you can use that. So it can actually read, if the number of bytes available is greater than 0, you can read the byte 1 byte at a time with a serial.read. Or you can use a serial read line and get a whole line at a time if you like. But we haven't gotten that far yet. So then let's see, where were we? Question 18, I think. We just did 16 or 17, I think. And then question 18 says, if there's any serial data, read it. Look for the next. Oh, here's something new. Serial.parseInt. Serial.parseInt. What does that do? ParseInt. So instead of serial.read, we're going to do serial.parseInt. And then what we're going to do is we're just going to print out the integer. Let's see if that works. ParseInt. Uploading. Okay, that's 1, 2, 3. enter. 1, 2, 3. It worked. What if I said b plus 1? I made an adding machine that adds 1. I guess that's a suitable application for an 8-bit toaster controller. 1, 2, 3. Prints out. What's taking so long? Do I need a line ending here? 1, 2, 3. Enter. Ah, here, 1, 2, 3, 4. And it prints out a 1. What's going on here? Oh, I guess because the carriage return, right? The carriage return came in. Should say no new line ending. 1, 2, 3, 4. 1, 2, 3. There it is. 1, 2, 3, 4. 1, 2, 5. Boy, this is slow. I must have too many things going on. So there it is. You've gotten as far as question 18. We're almost done, I think. You guys can finish up the rest. That was very fun and educational. And the answer to question 18, he says, the above code will print out the number and 0 unless no line ending is used. So the 0 comes in when there's something of a line ending for printing out this decimal thing. So he's printing out the actual conversion of the character into an int, and it's a non-visible character, so it comes in as 0. So if I have carriage return, what is he printing out? 90, enter. Yeah, he printed out a 1. What if I had a new line? 90, enter. Still printed out a 1. So it's not printing out a 0. Is he printing out a 0? It's not. This is number 19. Which number is this? 18?
Yeah.
Yeah, it's not printing out a 0. It's printing out a 1. Oddly enough. So we'll modify that. That should either, it should say printing out a 1 unless no line ending is used. So that'll be true once I modify it, in case somebody's already taken this test. So I'll make it so that it is true, because that's what the answer key says. But according to my test, this should be a 1 and not a 0. So that's what we have time for today. Hope you liked my little presentation. You guys stay safe. We've got a homework due tonight.
Thank you.
Thanks a bunch.
Professor.
Thank you.
Thank you.